Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
This is a recognition of the work in computational thinking that we've been doing with CMU, I think now for 6 years. Is that right, Harold? Yeah, 6 years. 6 years, yes. So it's a very interesting set of talks. We have Randall talking first, and then Golan Levin talking from the College of Fine Arts, Ariel from Computer Science, Guy and Frank all from Computer Science. And I look forward to learning about what you've been doing about computational thinking. And this afternoon and tomorrow morning, we have our mind swap on large-scale computation for large-scale machine learning. This is really a hot topic, as you know, for both academia and industry. And not all the Microsoft researchers could attend, but we'll have a virtual discussion, I hope, when they can attend virtually. So it's my privilege to introduce Dean Randy Bryant, who has been a long-term partner with us at CMU. And Randy has a long and distinguished history and has achieved widespread recognition for his work. He's a fellow of the IEEE and ACM, as well as the National Academy of Engineering and the American Academy of Arts and Sciences, and has won an impressive array of awards and contributing to the development of the symbolic model checking, as well as things like electronic design automation. So I look forward to hearing what Randy is going to tell us about computational thinking, and I just reread the other day Jeanette Wing's CACM article on computational thinking. So I'm very keen to hear Randy talk about Center for Computational Thinking. Randy.
Thank you, Tony. I thought I'd start off with a bit of a historical perspective on this because the center really started 6 years ago, and the idea of computational thinking really arose a little bit earlier than that, around 2005, 2006. And by the way, I'm doing my best to channel Jeanette Wing in all of this because she really is the person who pulled that all together and pulled together this center. And so I'm doing my best to imitate her, although I know my hair isn't long enough or black enough. But just to kind of take you back, not that long ago, temporally, but very long time ago, thinking-wise, in 2005, the computer science in academia, we were in sort of a state of demoralized state in that it seemed like nobody loved us anymore. In particular, as you see this chart, those blue bars show how many applicants we had to the computer science undergraduate program here at CMU. And it had peaked at the dot-com boom and then dropped by almost a factor of 2 in just a few short years as part of the dot-com bust. But at the time, it seemed to be more than just a normal boom-bust cycle. It seemed like something fundamental had gone wrong in that young people, which always had been sort of, computer science has been this magnet for young people, including most of us, since the beginning of computers, and always attracted really smart people. At least we like to think of ourselves as smart. And we never had to like go out and do any kind of recruiting because people would come to us. And yet here it seemed like things had fallen away. And there was a sense of this sort of malaise that computer science has run its course. Now there's new and more exciting things to do. And this is going to lead to, at best, dead-end careers you might be paid 100 rupees a day to do. And you know, you'd be stuck as a coding monkey in some cubicles. And also, you know, all that, you know, computer science did some pretty cool stuff. We've got email, we've got the internet. but that's kind of it. I mean, there's nothing much going to happen anymore. So that really was this sort of something of a viewpoint going on there. And people, including Jeanette and others, really started to think about, well, what's wrong with this picture, and what do we need to do to better express the idea that we're not just a bunch of coding monkeys, that there's something about this subject that's actually very deep intellectually, very challenging, captures a lot of understanding and thinking, and writing the code is just a sort of final expression of a very long process of coming up with the right algorithm, the right structure for the program, and so forth. And also the sense that there's more about what we do that's applicable not just to creating better programs, but sort of this way of reasoning about systems and computing agents that is actually applicable beyond our own domain. And finally, that there's another possibility that this isn't just a dead-end thing. There's plenty of jobs. And there's a very good study done by people with the ACM, with Moshe Vardi in charge, where they actually did a pretty serious study of the global software industry and showed that even though it had expanded tremendously in other parts of the world, the actual number of jobs in the US in this area had stayed the same, slight decrease during a recession, but all the predictions were it would be probably the largest sector of growth for the jobs in the future. So that sort of gets you the picture of, say, around 2005, 2006. And so Jeanette wrote, as Tony mentioned, this essay in CACM, which was when she kind of went public with this message of computational thinking, of a way to capture and bundle up this sort of intellectual core of computer science and say this is a very important area, and it's not just some superficial set of tasks. So the whole idea of computational thinking is there's many different variations on this theme, but for example, we started sending out to our prospective undergraduates brochures that said, come to Carnegie Mellon, study computer science, learn computational thinking. And I think this is actually a fairly good summary. It says CT, computational thinking, is how computer scientists determine what can be computed and how to compute it. By looking at the world through the lenses of algorithms, abstraction, Carnegie Mellon computer science, this will be problem solvers for the 21st century. And so that's sort of a core idea that we used both to describe who we are and what we are. And then the idea, as I said, is this is a way to express what we're doing and why our discipline is challenging, fun, and exciting to the rest of the world. And also this idea of, hey, a lot of what we want to do, what we've been doing for years, are actually good design principles that could be used in solving other complex problems. So I think, again, a lot of this question about what is computational thinking, I've heard various different takes on it, but I thought this was an interesting one because some people go, well, isn't computational thinking just mathematical thinking? Isn't it just algorithmic thinking? Isn't it just systems engineering thinking? And I think the answer is it's got a little of all of that, but that's not all that it is. So in particular, there is this idea of an algorithm. That's obviously something that we all know, believe, and understand deeply, this idea of extracting out of some problem a sort of core mathematical structures that we're trying to compute or create, and then designing the best possible way to do that and analyzing it as well. But there's also logical thinking, and I'll mean logical in two ways. One is sort of layered abstractions, system design style, that you have interfaces that are the specification that are distinct from the implementation, and so forth. And the other is the logic of programs and program execution, reasoning about programs, invariants, and other properties like that, as well as type theory, the logic of programming languages. And then there's certain elements in system design that we've come to understand well. This idea of as much as possible, trying to loosely couple your parts, make things, think from the very outset how you're going to scale from this size to 10 times larger, to 100 to 1,000 times larger. We've dealt with these huge range of dimensions to our problem, much more so than you'd have in the physical world. The idea that our system components are inherently unreliable, but we want to make highly reliable systems out of there via various forms of redundancy and fault tolerance. So all those sort of principles that a good system designer knows and understands. And I think part of the idea of computational thinking in this effort was to all these kind of unwritten principles that were sort of scattered around and we'd all ingrained in us through our careers, to try and condense that into something that could be expressed and described to other people. So that was sort of the starting point of the Center for Computational Thinking. And of course, it's also designed to be a very collaborative effort between Microsoft Research and CMU, looking into new problems, new challenging research areas where there's a sense that these are of mutual interest. And so in particular, there's a steering committee. The idea for the projects is that faculty would propose projects using a very short kind of proposal, but they'd be reviewed by a steering committee that included people both from CMU and MSR to decide which ones to actually fund. And then also a way to engage more directly one-on-one via mind swaps. In other words, sort of little workshops to bring people together on particular themes and find where there's sort of share ideas and formulate plans for how we could go from there. So in particular, going back through the schedules, the kickoff was not really a mind swap. It was a series of presentations, but each had a CMU person and each had a Microsoft person, sort of describing some general theme and area and what promising types of research there were. And then there were 2 actual mind swaps, and then there's another one later today where it really was researchers from CMU and researchers from Microsoft getting together and fairly closely interacting and sharing ideas. So the first set of them then included a discussion about, it was titled Computer-Human Synergies and Automated Creativity. And so in particular, it was the ideas of human computation and things that we now call crowdsourcing and ideas like that, of having computers as part of the, humans as part of the computing agents in addition to humans. The second was on type theory and program logic. And the third presentation was a general area, I'd say, I sort of bundled it all up, auctions, game theory, and algorithms, meaning bringing in some of these principles into computer science. The fall 2007 was about privacy, and in particular, the sort of technical aspects of privacy, for example, differential privacy and other metrics like that, as well as the human side. So how do humans understand their privacy settings in different applications? How do you capture their desires and the risks of privacy? And then the more recent mind swap was about the relation between computer science and economics, how we can bring the principles of economic theory into computer science, and how computer science and algorithmic and computational thinking really can influence economics as well. And that overall, if I look back at the projects, I'd say that those sort of different themes come out as the different types of activities that have been done here over the years. So this idea of economic principles and concepts coming up with new ways of solving CS problems and vice versa. Privacy, I'd describe it as expanding horizons. So this idea of computers and the way we think about things can be used not just to solve our own problems, but even well outside the boundaries of traditional computer science. And then another major component of the work has been on CS education. So how can we introduce students earlier on in a more systematic way to some of these principles of computer science rather than it being something they sort of accrue over a lifetime of experience. And in fact, today we'll have presentations that cover many of these subjects. And so I'm not going to try and go into any technical details because you'll hear it from the other presenters. And so just to list some of the projects that were done over these years in this general area of CS and economics, there's been work on setting up, and we'll hear about that, exchange systems, ways of improving the sort of using economic principles to control the allocation of resources in a computer system, how to think about games as a way of designing a protocol, and the sort of algorithmic aspects of the marketplace. In the area of privacy, as I mentioned, it sort of goes from the spectrum of sort of the technical aspects of privacy, metrics for privacy, as well as how this is sort of the human aspects of it. And then expanding boundaries, there's been, well, some of those projects I already listed. You could argue kidney exchange is definitely expanding the boundaries of computer science, but also new ways of doing drug design, new ways of having a computer system set up to be an accompanist with live musicians. Go On, as we'll hear later today, has done quite a bit of work that sort of spans between education and this externally focused. How do you get artists using computer technology to be able to express new, different ways of artistry? And and then on the educational side, this whole area of computational thinking has had a pretty major influence on how we teach our undergraduates. And so in particular, there was a major curriculum revision that we started in 2010, which had a couple of different, all at the sort of first year, 2 years of our computer science program, not just for our own majors, by the way, but even more so almost for our non-majors. So one was, because at the time we were teaching our especially the non-majors, we're just getting a single course in Java programming that really did not include much thinking. Let's put it that way, computational or otherwise. It was this is how you write Java programs, and so we really wanted to say, no, really, even if somebody only takes one course from us, we want them to at least have some glimpse of the underlying principles of our domain, and not just sort of this superficial understanding of some of its tools. But also, and as Guy will talk about later in these sessions, to bring in the idea of parallel thinking. So prepare students for a future in which most of their computer programs will run on multiple cores or multiple processors, and they need to be, even in their design of algorithms, have to be thinking about what works in a parallel setting versus a sequential one. We also, in the process, sort of migrated Java out of the introductory programming sequence with an understanding that Java, by the way, is I have not a negative statement about Java at all, but it's just not a very good language for introductory programming courses. And so it really should be moved into a different part of the curriculum. So just to sketch it out a little more, and these all look like numbers, but course numbers, but let me just outline to you. And these are the courses that would be taken by our majors, as well as many of the students in, say, ECE. And so it starts at the beginning level. We've always had a discrete math requirement. And for students who come in with no programming experience whatsoever, which is right now about 1/3 of our majors, interestingly enough, they take a course that is indeed an introductory programming course. It's in Python instead of Java, but it is pretty much basic programming. There's a separate course that I don't list here, by the way, which is for non-majors, that really is a sort of more kind of holistic view of computation. It includes programming, but it also is trying to bring in the bigger picture as well. But we figure with majors and with students who will take multiple courses, we can start them off with programming, and then we introduce more of the computational thinking as we go. So then above that, these two courses are sort of our true introductory programming courses, and one is about imperative programming, and Frank Fenning's going to talk about that later today. And then the other is in functional programming, which is something we've always taught, but we packaged it in a slightly different way and designed it to be more a 100-level course. And then those two courses feed into our course that Guy Block will talk about today, which is data structures and algorithms, but including this sort of parallel thinking about algorithms and not just sequential. And so in particular, we had to structure it this way because functional programming is actually a very important set of concepts if you really want to think about parallel execution. And that's why we arrange things this way. So I think the interesting thing, back when people were going through this sort of self-evaluation of computer science, there was sort of a prevailing view that, you know, if we have to kind of dress up this thing and make computer science more jazzy and put in multimedia and, you know, make game programming and stuff in our introductory courses in order to attract students into our field, because otherwise they're just going to get turned off. And also, you know, students nowadays, they all want to program phones and do apps and stuff like that. So we should sort of be bringing in all this technology that would make them feel really edgy about, you know, I can program your phone for you. We actually do have them program phones, but, you know, this is sort of, they want to know the latest buzz. What's that thing out there? Our view is, in some ways, if you look at this, almost retrograde, saying, no, actually what we want to do is make our introductory sequence more rigorous, i.e. harder, and more mathematical, and because really, if you think about where the world is going and software is going, if anything, we've got to do a better job rather than making it cooler. So, you know, creating a commercial software nowadays is harder than it used to be because of issues, especially dealing with security. And if you've got a bug in your program, some bad guy is going to figure that out and exploit it as an attack method. So the whole area of programming, if anything, requires more discipline and more rigor now than it did in a former era. And also a feeling like, look, we're preparing people for a life, a career, and so it isn't really what is the latest buzz, what's the latest sort of methodology, but let's get some principles in there that even after they get their jobs, they'll be able to then carry through in their careers. So this has gone amazingly well. I won't say it's been absolutely smooth sailing, but this, in a sense, stepping up the rigor in our program, and this has affected not just our own majors, as I mentioned, but we have a lot of other students on campus taking computer science courses. And I think, actually, I'll credit our corporate partners for having helped make this possible. And the reason I say this is that when they go off to interview at Microsoft and at other companies, they get asked these incredibly hard and arcane problems in algorithms, logic, reasoning about programs, and all this stuff. And they come back and they go, wow, that stuff I learned in my algorithms course got me a job. And so they're pretty happy about that, and they tell their younger friends, and their younger friends say, sign me up. So it actually has been let me call it a virtuous cycle, at least among us nerds, to say that people have really understood that there is you know, you've set a high enough bar and sort of imposed this thinking about among our students that say, wow, this is pretty serious business, and we have to really prove ourselves worthy to get the kind of jobs we want to get. This is, by the way, a cover of a book about how to get a job at Microsoft. There's similar books about getting jobs at Google, getting jobs here, there, and everywhere that you can go. And if you look at them, they're just full of problems. They're actually pretty fun to look at if you're, well, if you're a nerd, but I am. So that's sort of the background, and just to sort of cap this off, this is the way the admissions look now. So you remember that first slide I showed ended in 2005 when we hit our low point. And since then, we've been climbing out. And in fact, for each of the past 3 years, we've broken all historic records. And we're on chart this year to break it again. And probably we're anticipating around 5,600 applications. So computer science flipped from being the job people didn't want to the job everybody wants. And this idea of spending all your time hacking code has become cool again. And that's great. But I think this core of bringing in these principles and presenting them to our students and also using them to guide us more systematically has been a very positive development. So with that, I'll finish.